Hi, Professor. My name is Vikas Reddy Chekuri and my partner Kuladeep Sai Varun Naroju. Here we are about to speak a project on completely fair scheduler. This is the overview of completely fair scheduler, and these are the topics we are going to cover in the next slides. CFS is the current task scheduling algorithm which Linux is using and was developed by Indigo Molnar. CFS is based on the rotating staircase, a deadline scheduler. It's called RSDL by Con Colivas. Almost 80% of the CFS algorithm was developed based on the concept of ideal fair scheduler. Its CFS has an elegant handling of input and output and CPU bound processes. Why CFS? Compared to the prior scheduler, like first come first serve, round robin, CFS is very efficient as it has a time complexity of big O of log n. Prior schedulers, time complexity has big O of 01. It runs based on queue and it uses linear data structure. In CFS, it runs based on red-black tree and it uses non-linear data structure. Ideal fair scheduling. Ideal fair scheduling is nothing but dividing the CPU time equally among the process. As I said before, 80% of CFS is implemented based on the concept of ideal fair scheduling. Let us say there are 5 processes in the ready queue. Now 100 by 5 equal to 20% of CPU time is allocated to each and every process. Ideal fair scheduling. Let us take an example of 4 processes A, B, C, D with burst time 8 milliseconds, 4 milliseconds, 16 milliseconds and 4 milliseconds. And let us say CPU has 4 milliseconds and there are 4 processes in the ready queue. So as per formula here 4 milliseconds divided by 4 equal to 1 millisecond of the processor time. Therefore A, B, C, D will execute for 1 millisecond. In similar way for second cycle each process will get again 1 milliseconds, and at fourth cycle you can see here in the slide have only 2 processes, so the 4 milliseconds divided by 2 equal to 2 milliseconds. So here I can explain you in a briefly way. So take a time of quantum of say 4 milliseconds. Initially there are 4 processes waiting in a ready queue to be executed, and according to ideal fair scheduling each process gets equally fair time for its execution time. So 4 milliseconds divided by 4 equal to 1 millisecond. Each process gets 1 milliseconds. Here you can see in the slide. After the completion of 4 quantum process, you can see here B and D has same milliseconds, are completely executed and remaining are A and C. So A and C, which are already executed for 4 milliseconds, and their remaining time is So A equal to 8 milliseconds and C equal to 16 milliseconds. In the fifth quantum of A and C will execute 4 divided by 2. Here you can see in the slide 4 divided by 2. 4 milliseconds divided by 2 equal to 2 milliseconds. This is ideal fate scheduling in which each process gets equally share of time quantum no matter what priority it is of. Incorporating idea of IFS in CFS, virtual runtime. CFS is similar as ideal fate scheduling. Instead, it priorities each process according to their virtual runnable time. Each runnable process have a virtual time associated with it in PCB. It is also called as process control block. Whenever a context switch happens, or at every scheduling point, if process has run for TMS, then virtual runtime is increased for TMS. Virtual runtime plus equal to T. Runtime for the process therefore monotonically increases.
CFS uses the red-black tree data structure for prioritizing the tasks. This red-black tree is a self-balancing binary search tree. This red-black tree always ensures that tree remains balanced during insertion and deletion. As it is a binary search tree, the left child node is always less than the parent and the right child node is always greater than its parent. Here, if you see in this figure, 8, which is the left child of 13, and 17, which is the right child of 13. In the same way, 1, which is the 1, which is the left child of 8, and 11, which is the right child of 8. In the similar fashion, the entire tree is built and the left part of the tree will have the value lesser than its parent node, like values lesser than its parent node, and the right hand side of the tree, like the right part of the tree will have the values greater than 13. So by arranging the tasks in this way, the leftmost node will have the least value among the tree. Here in this case, 1 is the leftmost node in the tree, so this is the least value in the tree, and in this way we can get the task with least virtual runtime. If you see this figure, each node has a particular number, which is the virtual runtime for that particular task. As per the red-black tree, we know that each task on the left has the low virtual runtime compared to the task on the right. So the leftmost node of the red-black tree is the task with lowest virtual runtime. So in this case, uh, as per this figure, 1 is the 1 is the node which corresponds to the task having the lowest virtual runtime. Therefore, the scheduler should pick the task to run next. In order to find this task, there are two ways which are possible. One is by traversing from the root node, that is from 13 13 to 8, from 8 to 1. Second way is by having a pointer like uh, having a pointer like min v runtime, that is the minimum virtual runtime, min v runtime. So whenever the scheduler need a context switch, can just look where the min v is pointing and can pick the task with lowest virtual runtime. So this choice of lowest v runtime can be done in order of 1, and therefore independent of the number of processes present in the red black tree. So at the end of the task, at the end of the time slice, if the process which is currently executing is still runnable and it is has the not block on the input or output, it has not exited, then it is new virtual runtime is compared based on the amount of time it has executed in the CPU. Then it is again inserted back to the tree as per its virtual runtime. Process of picking the process of picking the lowest virtual runtime and executing it in the CPU for some time, t milliseconds, let's say for t milliseconds, and at the end of the time slice, virtual runtime would be incremented by t values and it would be increased again into the tree. It is inserted again into the tree. So now it will be it will not go into the now after incrementing the virtual runtime, uh, it won't be at the left part of the tree. As the virtual runtime is increased, the the it would be appearing at the middle or at the right hand side of the tree. So uh, as the v runtime increases, the process moves from left part of the tree to the right part of the tree. So this ensures that all the process will have minimum virtual runtime, that is minimum v runtime. In this way, starvation is avoided. Why red black tree? Red black tree is a self-balancing tree which uses left rotation and right rotation operations to make the tree balanced, so that no path in the tree will have twice as long as any other path. Its time complexity for insertion, deletion, and searching is big O of log n. How red black tree works. First check whether tree is empty. If tree is empty, then insert the new node as root node with color black and exit from the operation. If tree is not empty, then insert the new node as leaf node with color red. Step 4. If the parent of new node is black, then exit from the operation. Step 5. If the parent of new node is red, then check the color of the parent node's sibling of new node. Step 6. If it is colored black or null, then make sibling rotation and recolor it. If Step 6. If it is colored red, then perform recolor. Repeat the same until tree becomes red-black tree. How red-black tree works. Let us take an example of inserting 8, 18, 5, 15 and 17 and see how insertion happens in red-black tree. Insert 8. Tree is empty, so insert new node as root node with black color. Insert
18. Now the tree is not empty, so insert new node with red color. Now insert 5. Tree is not empty, so insert new node with red color. Insert 15. Tree is not empty, so insert new node with red color. But here there are two consecutive red nodes, 15 and 18. So we use recolor operation to make red black tree. Here you can see the image after converting 18, which is in red color, to a black color. Now we can insert 17. Tree is not empty, so insert new node with red color. But here again there are two consecutive red nodes, 15 and 17, with a red color. So we need to, here we have to perform left right rotation and recolor operation to make the tree balanced tree. After performing the left rotation, the tree looks like this. Now we have to perform right rotation and recolor operation to make the tree a balanced tree.
How does CFS uses arbitrary? CFS uses to represent the tasks in arbitrary and to find which tasks to run next. Each task is stored in arbitrary based on its virtual runtime. Leftmost node in the tree will be one with least virtual runtime. When CFS needs to pick next task to run, then it picks leftmost node. Priorities and CFS. Priority is used to weigh the virtual runtime. If process has run for t milliseconds and it added to the virtual runtime. A lower priority implies time move at a faster rate compared to that of a high priority task. Input output and CPU bound process. Input output bound should get higher priority and get a longer time to execute compared to the CPU bound. CFS achieves this efficiency. Input output bound process have small CPU bursts, therefore will have a lower virtual runtime. They would appear towards the left of the tree, thus are given higher priorities. Input output bound process will typically have larger time slice because they have smaller virtual runtime. How new process is created. Initially, it starts with minimum virtual time, therefore placed to the leftmost node of the tree, and this ensures that it gets to execute very quickly. So as it get execute, whether it's an interactive or a CPU bound process, its position within the arbitrary would vary. This was a brief introduction to the CFS scheduler, which is the default scheduler in the current versions of the Linux kernel. Thank you.